Hey! Welcome back to my channel. So, for the most distant galaxies, we're looking back in time, almost to the Big Bang. Imagine looking up at the night sky only to find it empty, no stars, no galaxies, just darkness. Now, what if we tell you this wasn't just a figment of imagination? What if we tell you that over 700 trillion stars vanished from the universe, leaving scientists baffled and the world in awe? But wait, there's more. Some emerged from this cosmic void, something beyond our wildest imagination. This isn't your average cosmic mystery. However, this discovery will put to the test all we previously believed to be true about the cosmos. We're going to go on an expedition into the depths of space where the impossible becomes conceivable and the unthinkable becomes real. Are you prepared to venture into the unknown realms of time and space? Join us as we unravel the mystery of how over 700 trillion stars suddenly vanished and the extraordinary phenomenon that emerged in their wake. Stars don't magically fade away, do they? Astronomers have held the view that celestial lights are static and unmoving for a very long time. Astrophysicists have long assumed, even after it became apparent that these lights were real objects similar to the Sun, that they undergo extremely slow, dramatic changes over millions or billions of years. Supernova explosions are the unmistakable cosmic beacon that marks the passing of the most massive stars in the universe. These stars are many times heavier than the Sun and undergo sudden and catastrophic changes as they near the end of their lives. The explosions can be seen for months and can even be visible across hundreds of millions of light-years. What if, nevertheless, some stars abruptly fade into oblivion? This seems implausible given what we know about stars. But a team of astronomers has been analyzing data from decades of observations in an effort to determine if the seemingly impossible does, in fact, occur. Finding objects that shouldn't be feasible is the mission of a worldwide team of astronomers. VASCO, or the Vanishing and Appearing Sources During a Century of Observations project, said Beatrice Will of the Nordic Institute for Theoretical Physics, Sweden. We're actually interested in all kinds of vanishing objects. But ideally, I'd like to find a star that's been steady and has been there in the sky for as long as we can remember, and as long as we have data for, and one day it just vanishes. You can point the biggest telescopes in the world at it and still see nothing there. Since Will and her colleagues began work on the project in 2017, they have attracted a lot of attention from scientists who see the potential in searching historic records. We have astronomers from all kinds of different fields interested in the project, specialists in active galactic nuclei, the power source of intensely brilliant quasars in the distant universe, stellar physicists, and CD scientists. Everyone has their reasons for getting involved. That doesn't mean all stars remain bright all the time, though. Our present knowledge implies that stars change extremely slowly and that sudden disappearances should leave behind evidence. The sky is really teeming with stars that may be seen to pulse and fluctuate in brightness, Will emphasizes. VASCO is about something different. We want to find something that goes from a completely steady star to just vanishing entirely. This hasn't been documented, and it's the kind of discovery that could lead to new physics. The advent of fully automated telescopes in the last several years has allowed astronomers to catalog the sky at a rate that was previously unimaginable. Mount Palomar in California is home to the ZTF Zwicky Transient Facility, which is a combination of the historic Samuel Oskin telescope with a cutting-edge camera. It can scan the Milky Way twice nightly and cover the entire Palomar sky in just 3 nights, thanks to its extremely broad field of view. This greatly enhances the probability of spotting transients, which are explosive bursts of light that can originate from faraway stars, stellar flares, or be linked to extremely rare and violent cosmic events like enigmatic gamma-ray bursts. Projects like the ZTF work on very short timescales. But if you have a very rare event where something vanishes from the sky every 100 years, then you really need a very long timescale to pick it up. In our case, we want to find a star that has vanished or actually appeared using as large a timespan as possible, combined with the best catalogues from older times, Will notes, emphasizing the significant distinction between the two types of star discovery. Contrary to expectations, the team's quest for reliable historical data brought them full circle to Palomar and the Samuel Oskin telescope. This particular telescope had previously supplied the photographic plates for an all-sky survey in the 1950s, which the U.S. Naval Observatory, USNO, has scanned. Information gathered from the Panoramic Survey Telescope and Rapid Response System, PAN-STARRS, at Hawaii's Haleakala Observatory was utilized to create a contemporary analog. Any method that yields data will do, Vail states. The idea is that interested parties may visit the site to assess the photos, and if they have any questions about a particular instance, they can post a remark. The team has to verify and examine all objects in the USNO catalog that are marked as having no obvious known star counterpart. Then they check the shape, brightness, and other properties to see if it's a defect on the original survey's photographic plates. GIA, operated by the European Space Agency, is presently collecting precise data for over 1 billion stars in the Milky Way, and the team also analyzes candidate data with this information. Although there isn't a perfect match for Vel's ideal object, a vanishing act by a long-lived stable star, many of the observed candidates are intriguing in their own right, and the survey has so far delivered over 800 stars that are supposedly missing. Many of these stars still require processing and in-depth study. Some short-lived transients have been studied and found not to be M-dwarf flares or supernovae. Vel continues, these transients make up the majority of what we have discovered so far. But there are other things about which we are still uncertain. The other less probable possibilities are variable stars, cataclysmic variables, or novae, which are explosions on the surfaces of white dwarf stars and binary systems. None of these sources are located near a known variable, and certain modern surveys should detect the companion star in a nova system faintly, even if the white dwarf itself is invisible. It is anticipated that these high-energy cosmic eruptions will briefly become visible as their energy output decreases, suggesting that they may be optical afterglows from gamma-ray bursts or fast radio bursts, which are still poorly understood. Such bursts are expected to have extremely large amplitudes of approximately 8 to 10 magnitudes, but they disappear after a few minutes and do not appear to have any detectable counterpart when we examine the same regions with large telescopes. Obviously, there is still a lot of work to be done with 800 candidates, and it's likely a diverse collection of objects. If those 800 candidates turn out to contain an ideal vanishing star, what could be the possible explanation? A failed supernova could be one possibility. This would be a so-called star whose core is so dense that it collapses into a black hole, devouring the star's outer layers in the process. The star would then no longer undergo the nuclear fusion that typically accompanies a supernova explosion, and no visible remnant would remain. Nonetheless, according to Vel, the chances are not in favor of this theory. She determines that such occurrences ought to occur approximately every 3 centuries in our galaxy, rendering the possibility of the Vasco project accidentally discovering one improbable. Currently, other natural processes that could cause a star to simply vanish are not easily conceived of. Until a candidate with observable properties arises, there is little use in speculating on potential new physics that could be involved in this cosmic vanishing act, Vel concludes. More and more powerful computers and larger and more sensitive telescopes have ushered in the big data age of astronomy, leading many steady researchers to believe that the otherwise inexplicable behaviors of stars and other objects are more likely to reveal the existence of aliens than radio signals intentionally or unintentionally sent our way. The idea is that as long as societies progress far enough, eventually some of them will figure out how to engineer stars so that they look different in ways that we can't explain. The classic case in point is the Dyson sphere, a halo of power plants in orbit around a star that would be the most efficient way to get energy from a star. According to science fiction writer Arthur C. Clarke's third law, any sufficiently advanced technology is indistinguishable from magic. In the absence of any known natural explanation for a star's disappearance, the intervention of intelligent aliens would almost certainly appear to be the most plausible alternative to the supernatural. With regard to Vasco, there are several different ways of thinking about it, Vel said. Dyson spheres and other structures, beacons that are turned on and off or point in our direction for a certain time, or maybe there are ways for a civilization to actually get rid of stars that are getting in the way. Even the red transients that the team has identified so far could have a possible artificial cause. Of course, the first hypotheses we go for are natural ones, and we don't have any reason to exclude those yet. But if I was in my extraterrestrial speculation mode, I guess a laser beam could also produce a red transient of this type. In the meantime, the Vasco project is ongoing, with many of the candidates identified so far awaiting proper confirmation and analysis. Only a quarter of the sky has been checked so far, and further progress will hopefully be accelerated by more volunteer citizen scientists and new automation methods currently being developed in collaboration with the Spanish Virtual Observatory. V hints at exciting discoveries that have already emerged from the data and await formal publication. As far as we are aware, no process has ever been witnessed in nature where a star would simply vanish, with the exception of this hypothetical failed supernova. The primary motivation for studying vanishing stars was to seek the seemingly impossible. At the same time, space-time holes may exist, but humanity's telescopes can't see them. If they do exist, the fissures are very, very ancient artifacts from a period just after the Big Bang when the cosmos had just begun to cool down from a hotter, more exotic state to the cooler, more familiar one we observe today. According to this theory, the Great Cool Down or phase transition began earlier in some regions than others, and bubbles of the cooler universe formed and propagated across space until they intersected with other bubbles. At last, all of space underwent this cooling process, and the older universe vanished. It was speculated by some physicists that the cosmic microwave background, CMB, could still contain traces of the old high-energy state at the boundaries of the bubbles, where the space-time fabric was imperfectly fitted at the points where the cooling regions intersected, heat remaining from the tumultuous birth of the universe. However, as stated in recent research, such evidence would be indistinguishable from background noise for any telescope to detect. A physicist from McGill University in Montreal, Oscar Hernandez, stated, "Cosmic strings are hard to conceptualize, but they do have terrestrial counterparts." Have you walked on a frozen lake? Have you noticed cracks laced through the frozen lake ice? It's still quite solid, there's nothing to be afraid of. But there are cracks. Ice is water that has gone through a phase transition. Water molecules were free to move as a fluid, and then, suddenly, somewhere, they start to form into a crystal. As it progresses, it begins to cover itself with tiles, which are typically hexagons. Picture this, you have tiles that are precisely hexagonal, and you tile the lake with them. There is almost little chance that your tiles will match up if someone on the opposite side of the lake starts to tile again. Just like cosmic strings, the fissures grow via a phase transition mechanism. Long fissures are formed by imperfect meeting points on the surface of a frozen lake. These, in the fabric of space-time, generate cosmic strings. If the underlying physics is true, it is believed by researchers that fundamental force and particle behavior are governed by fields in space, which were created during the initial phase transitions of the cosmos. There could be a field relating to some particle that has to, in some sense, pick a direction to freeze and cool in. And since the universe is really big, it could pick different directions in different parts of the universe, he said. Now, if this field obeys certain conditions, then when the universe has cooled down, there will be lines of discontinuity. There will be lines of energy that cannot cool down. Those nexuses would seem like incredibly thin lines of energy traveling through space. If we saw them now, an additional piece of proof that physics is larger and more complex than the current paradigm would be the discovery of those cosmic strings, which would be a major deal. Currently, the Standard Model incorporates not just the elementary particles like quarks and electrons that compose atoms, but also more exotic ones like the Higgs boson and neutrinos, and is considered to be the most advanced theory of particle physics that has been verified. On the other hand, the majority of physicists hold the view that the Standard Model is incomplete and that there are various ways to extend it, such as supersymmetric particles, also known as the Stowe-Slepton, or superstring theory, which states that all particles and forces can be described as vibrations of small multidimensional strings, Hernandez said. Many extensions of the Standard Model that people really like a lot of superstring theories and others, naturally lead to cosmic strings after post-Big Bang inflation takes place, Hernandez said. So what we have is an object that is predicted by very many models. So if they don't exist, then all these models are ruled out. And if they do exist, oh my God, people are happy. Ronica of Metropolis College in Westmount, Quebec, and Hernandez had previously contended that the most effective method for detecting the strings in CMB would be to use a convolutional neural network, a highly effective pattern-finding algorithm. In a different 2017 publication, they stated that presuming an ideal noise-free CMB map, a machine programmed with that type of neural network should detect cosmic strings with extremely low energy levels or tension. However, returning to the topic in this new paper, they demonstrated that in fact, it's highly unlikely that we can provide clean enough CMB data for the neural network to identify these potential strings. Other brighter microwave sources mask the CMB and are hard to completely detangle. Even the most advanced microwave instruments have limitations in resolution and recording accuracy that vary randomly from pixel to pixel. Combined with other factors they discovered, therefore, this approach to searching for cosmic strings is a dead end. Still, they expressed hope that things would turn out okay. Using measurements of the cosmos's expansion in all directions across early universe regions, a new method for cosmic string hunting has been proposed, which is referred to as 8.3 intensity mapping. Unlike previous methods that relied on studying individual galaxy motions or precise CMB images, this method relies on measurements of the average speed of hydrogen atoms separation from Earth in all regions of deep space. The top 8.3 intensity mapping observatories, so-called because hydrogen's electromagnetic radiation has a distinctive 8.3-meter wavelength, are not yet operational, but the scientists expressed optimism that stronger evidence of cosmic strings will be found in their data upon their arrival. At that point, the search can start again. Thanks for watching another episode of Space Voyager. While you're still here, make sure to click the video on your screen for more mind-blowing videos about space.